Hello everyone, this is Dr. Webb. So in our last two videos, we introduced the idea of a limit, and then we gave a more rigorous, firm mathematical definition for limit. What we're going to turn our attention to next is how to actually calculate limits. So in this video, we're going to be going through some rules for limits that are going to help us do that. And so let's just recall, if we say that the limit of f of x as x goes to a equals L, well, the intuitive idea of this is that as x is getting closer and closer to the value of a, the values of f of x are going to be getting closer and closer to L. And rigorously what we mean is that if we take some small value epsilon greater than 0, then we can find some small value delta usually, or usually delta is small, such that when the distance between f of x and L is less than epsilon, and so again recall this absolute value right here, this is looking at the distance between f of x and L is less than epsilon. So the distance between f of x and L is small. Whenever the distance between x and a is less than delta. So this is talking about distance between x and a. And in this one, I included in that we want this absolute value to be bigger than 0. And it's because we don't really care what happens when x is a. We just want x to be different from a but small. Okay, so we are going to use this idea to start working out some limits. Okay, so first, what if we took the limit of just the constant function 7 as x goes to 3? Okay, so in this case, f of x equals 7. X is going to 3, so a is 3 in this case. So what do you expect is going to happen to a constant function as you move around the x values? Well, constant function, the whole idea of a constant function is that it doesn't change. And so what would we expect our limit to be here? Well, we'd expect our limit to be 7. Right? Because the function is always 7. So let's see if we can verify this rigorously. So let's let epsilon be greater than 0. And so then we want to look at for what values of x is f of x minus L less than epsilon. Well, let's plug these in. And so f of x is 7. L, our guess for the limit is 7. And so we want that to be less than epsilon. But what's 7 minus 7? Well, 7 minus 7 is 0. And at the beginning we said epsilon is greater than 0. So when is epsilon greater than 0? This is always true. So delta can be anything. So what this means is that for any x value, the distance between 7 and 7 is equal to 0, which is less than epsilon. And so delta can be anything. And so this tells us that the value of this limit is 7. And so this verifies that L equals 7. So we can put that in and say L equals 7. Okay, so what if we did this more generally? We take some constant function, f of x equals c, and look at what happens as x goes to a. Well, we can do the same thing that we did before, right? We expect the limit's going to be c, and then when we look at c minus c, that's going to be equal to 0, which is less than any positive number epsilon, right? And so that's enough to say rigorously that the limit of a constant function is the value of that constant. Okay, let's make this a little bit harder. What's the limit of the function f of x equals x as x goes to 5? Well, if you talk this through, this seems a little silly. What value is x going to as x goes to 5? Well, it should be going to 5. So let's talk this out rigorously why this is true. So our guess, so in this case, f of x is just x. A here is 5. And our guess for the limit is 5. Okay, so if we let epsilon be greater than 0, and then we want to know for what values of x makes x minus 5 less than epsilon, well, as you can see from the rigorous definition, this is exactly the same statement we want for delta. So just let delta equal epsilon. So then if x minus 5 is less than delta, well, then x minus 5 is less than epsilon because delta and epsilon are the same thing. And so that gives us our rigorous check. So L is equal to 5. Okay. And in general, if for any value a, if we take the limit as x goes to a of x, this is always going to be a. And there we are. So now let's talk about some more general limit arithmetic. So let's start off with two functions. We're looking for both of these, we're looking at the limit as x goes to a. And for a function f of x, as x goes to a, it goes to the value L. And for g of x, as x goes to a, it goes to the value m. Well, what would happen if we added f of x plus g of x together? Well, f of x is getting closer and closer to L. G of x is getting closer and closer and closer to m. And so when we add them together, you have something really close to L plus something really close to m. They're going to be getting closer and closer to L plus m. And that's what we're going to get. I'm not going to go through the rigorous proof of this. We could toss in some epsilons and deltas and do this, but it comes out to exactly what you would expect it to be. What about if we did multiplication instead? So if f of x is getting closer and closer to L, g of x is getting closer and closer to m. If we then multiply them together, something close to L times something close to m, it's going to end up being close to L times m. So the product of the two is going to go to the product of the limits. Next, let's do f of x minus g of x. So if f of x is getting close to L, g of x is getting close to m, something close to L minus something close to m is going to give us L minus m. And then lastly, if m is not equal to 0, and we look at the ratio of f of x divided by g of x, so f of x over g of x as x goes to a, well, so long as m's not equal to 0, we're going to get L over m. So all of this just makes sense. Once you know the limit of f of x and g of x individually, we can do this basic arithmetic, adding, subtracting, multiplying, dividing, so long as it makes sense and it plays well with the limits. So let's use these to do some limits. So what if we're taking the limit of the function, it's the line 5x minus 4 as x goes to 3. Well, so we've got some subtraction here. And so we could break this down to be the limit as x goes to 3. Let's clean that up a little bit. of 5x minus the limit as x goes to 3 of 4. That's what the subtraction rule said, that we're allowed to break this up. Well, 4, this is a constant function. We did limits of constant functions. So this is going to be 4. The 5x, that's a product of limit as x goes to 3 of 5 times the limit as x goes to 3 of x. And so 5 is a constant, so it's going to 5. X, well, we're taking the limit as x goes to 3 of x. That's going to be 3. And then at the end, we're subtracting off 4. So 5 times 3 is 15. Minus 4 gives us 11. So using this arithmetic, we can break this down, break it down by the subtraction, pull apart the 5 and the x, and do each of these separately, do each of these limits separately, get the values, and then put them back together to get the answer. So the limit of 5x minus 4 as x goes to 3 is 11. And there we have it. So the same idea we can use basically on any line, right? So if we looked at the limit of just some general line, mx plus b as x goes to a, we can break it up the same way that we saw before. Right? The limit of m as x goes to a, that's just a constant, m. The limit is x as x goes to a. Well, we figured out that that's always a. Plus the limit of b as x goes to a. Well, b is just a constant, so that's giving me a b. And so we end up with that we get back ma plus b. Or this is what we would get when we just plug a in for x. And so the limit of the line, it's exactly what you would expect it to be. You just replace x with a. Okay. What if we wanted to do the limit of x squared as x goes to 4? Well, we could do same idea as before. For squaring something, what are we really doing? Well, we're multiplying x by itself. And so we can think about this as being the limit of x times x. And we know how to do the limits with multiplication. So we can think about this as being the limit as x goes to 4 of x times the limit as x goes to 4 of x. And then we've worked out both of these limits, what these both have to be individually. They're both going to have to be 4. And so the answer at the end is 4 times 4 is 16. So what's the limit of x squared as x goes to 4? Well, really, at the end, we can just plug that 4 in, square it, and pop out 16. And so the rules say that's completely legal to do. And in fact, if we were taking x to the n, where n is any positive power, actually it could be positive or negative. So here n is any integer, because we can get x to the n by just multiplying and dividing. So n can be negative so long as a is not 0. Negative if a is not equal to 0. So we can divide. This is going to work out to be exactly what we want it to be, right? X to the n, really we're just multiplying x together n times. And so this is going to be equal to the limit as x goes to a of x raised to the nth power. And limit of x goes to a of x is just a to the n. And so we get exactly what we'd expect, a to the n out of this. Okay. And so in fact, once we can do powers of x and we can do multiplication by constants, then that means now we can take the limits of any polynomial. So this p of x here, this just represents a general polynomial to the nth power. And so the bn's, the bn minus 1, all of those are all the coefficients. And so how do we take the limit as x goes to a of this polynomial? Well, we can just plug a in for x anywhere, because all we are doing, all this involves is multiplication and addition between x's and constants. And so since we know how to take the limit of x by itself, and we know how to take the limit of constants, and we know how to deal with multiplication and addition, this tells us that we can do any polynomial we want. So we can say, what's the limit as x goes to minus 1 of x cubed minus 2x plus 5? We just plug in minus 1 in for x, so this is going to be minus 1 cubed minus 2 times minus 1 plus 5. And so minus 1 cubed is minus 1. Minus 2 times minus 1 is plus 2 plus 5. So this is 5 minus 1 is 4. And we're done. And so, I mean, I think that really shows, how powerful these just couple of small examples that we did are. Just by understanding rigorously what the limit of a constant is, and understanding rigorously what the limit of x is as x goes to a, and then accepting these rules for addition and multiplication, subtraction, etc., now we're able to do a pretty big class of functions, a very important class of functions. We can now do any limit with polynomials. Okay, one more really important rule, and it's so important I'm going to put it up there as a theorem. So in this rule, we're going to suppose that we have two functions, f of x and g of x, and that they're equal everywhere except when x is equal to a. So perhaps f of x is not defined at a, but g of x is. And so then there's two possibilities. Either their limits as they approach a are the same, they're equal to each other, or neither limit exists. They both don't exist as x goes to a. Okay, and so this theorem is what's going to allow us to work out limits with rational functions. And so this is what I mean. Let's consider this limit, x squared minus 5x plus 6 over x minus 2, and we're taking the limit as x goes to 2. So just looking at this, our function f of x here is not defined at x equals 2, because then we'd be dividing by 0. So this is our f of x, not defined at 2. Right? But we can factor the top here. And so the top, I believe, factors as x minus 2 times x minus 3, right? X squared minus 2x minus 3x gives me minus 5x. Minus 2 times minus 3 gives me 6. So that works out. For x minus 2, right? So note that whenever x is not equal to 2, x minus 2 is not 0, and so then we're allowed to cancel out. So when x minus 2 is not equal to 0, and so that's when x is not equal to 2, then this equals just the function x minus 3, right? Because the x minus 2 divided by the x minus 2, we're not dividing by 0, so we're allowed to cancel, right? And so x minus 3, this is equal to our original rational function for all values except specifically at x equals 2. And so by the theorem, we're allowed to then swap it in to the limit. Take the limit as x goes to 2 of x minus 3. So we can plug 2 in there now and get 2 minus 3, which is equal to minus 1. And so this now has allowed us to take the limit of this rational function that has a hole at x equals 2. That is all for this video. I will see you again soon.